Streaming already working, up and running. All right. So thank you very much, friends and colleagues, for being here today. Thank you very much, Andrea, for joining us and give us this seminar. Andrea Iannelli, he did a bachelor and a master thesis on aerospace engineering at Pisa. Then he moved to UK, to University of Bristol, to do a PhD with our colleague Andres Marcos. And after that, 2019, he moved to Switzerland, to the ETH Zurich, where he's doing a postdoctoral fellowship. His research interests have to do with control, robust control, and recently data-driven control. And he's going to be talking today about it. So, Andrea, welcome. Thanks, and the floor is yours.
Thank you, Manuel, for the introduction, and thanks everyone for attending this talk. Thanks for inviting me also to Madrid. It's always a pleasure to come to this beautiful city and share my research with you, and also interacting with researchers and learn what you're doing. Today I'd like to talk to you about one of our recent works titled The Balanced Mode Decomposition Algorithm for Data-Driven LPV, Low Order Modeling of Aerospace Systems. It's a rather long title, and I'll try to break it down and explain the single parts. This is a joint work with colleagues, Urban Fazel, which is now a postdoc at the University of Washington, and Roy Smith, who is my advisor at ETH. Since many of you don't know me, I thought of giving just a brief introduction, overview of my trajectory so far, which was also partially covered by Emanuele before. I was born in Ascoli Piceno, a little town in the central part of Italy. Then I moved to Tuscany, where I did my bachelor and master degree in aerospace engineering in Pisa. I had the pleasure to work for my master thesis with Professor De Masi and also with Rauno in the San Diego State University, where I learned a lot from them on aeroelasticity and fluid structure interaction solvers. Then I went back to Italy. I worked 1 year in industry on projects related also to aerospace applications, in particular tilt rotor. But then I decided that I wanted to do research, so I moved to Bristol, and there again I was lucky to come across Andres, who was my supervisor, together with also co-supervisor Mark Lowenberg, where I learned a lot about control and dynamical systems from them within an H2020 project called FlexOp. And then in the last 3 years, I've been working as postdoc in the automatic control lab at ETH Zurich. In addition to provide a bit of my bio, I also wanted to give a high-level picture of what are my research interests and where I see the interesting research challenges in the future. So my idea stems from the observation that doesn't only relate to control or aerospace, but in general to a lot of engineering fields, that there has been a paradigm shift in how systems are designed, and together with this, challenges come. So the paradigm shift is that we are always trying to go towards better performance on one hand, and also to address societal challenges on the other, such as climate change. And this forces us to consider systems of a different complexity than those that we have been dealing so far. And one of the consequences of this is that the classic paradigm in engineering of writing equations that describe any type of model is kind of falling apart, because there are some systems for which it's becoming increasingly challenging to be able to predict at any really level what is happening. So there is a strong shift, which of course was driven by advances in computer science, but that it's pervading also the engineering field in making use of data in order to not only ditch the modeling part, but I see as a complement of what we learn to do with first principles. So there is really this kind of need to come to terms with the use of data. And in my view, as I said, this is not something that will totally replace what we have been using, but I see it more as a complement. So the methods and tools that in aerospace engineering, or at least in the field that I feel closer to me at the moment, which is control, should adapt. But at the same time, without forgetting about the foundational principles and what brought us there. So going closer to control theory, I see as kind of a promising approach to deal with research in the future, this kind of view of standing on the shoulder of giants, which in my field and according to my background are topics such as optimal, robust, adaptive control, system identification, and dynamical system theory, which are really control theoretic fields, and blending them and trying to complement some of their shortcomings that are ubiquitous and any field is affected by them, with ideas, tools, and methods from learning. And of course, learning is a very big word. Fields that I've been looking at more closely in the last few years are statistical learning theory, optimization, and reinforcement learning, which have, I think, very close ties with control theory. And in the talk I'm gonna give today, hopefully you can see an example of this tendency to try to merge these two words, because in this algorithm, we are inspired by ideas from the learning community, but at the same time, we try to augment them with some system theoretic properties that often are not considered in these methods. And by doing so, we try to suggest some improvements, and they are also kind of verified numerically that there can be advantages in bringing together these two words. And these, again, are my two collaborators. So let's go into the outline for today's presentation. I'll start off by defining a bit more formally the problem statement and giving some preliminaries. Then I'll describe in more detail this BMD or balanced mode decomposition algorithm and explaining where these names come from. And finally, I'll show results which are obtained applying this methodology to a morphing wing demonstrator, which has been applied, or at least it's envisioned for airborne wind energy applications, which I think it's an application that interests some of you in the audience. So the motivation, the high-level motivation to go for methods that try to capture the best of the two words was given in the previous slide, but in particular, why do we want to use data to obtain low-order models is kind of briefly described here. So usually when you have a complex system, you need to have a very expressive model, which means that you need to resort to very high-dimensional representation of this system. And the standard approach is to first write down the equations, think about a fluid mechanics problem, where you have a lot of degrees of freedom, so you have a very high-dimensional problem. And if you want to control this system or simply have a fast way to do prediction, you need to have a lower dimensional representation that you can use. And so you have two kind of steps. The first is either using first principles or do identification to get a high-fidelity representation. And the second step is what I call the model-based model reduction. So you given a model which has nx states, you want to get another model which has nz states, where nz is much smaller than nx. And for this, there is kind of, for both steps, there are, of course, many different approaches. But the appeal of using a data-driven approach is to basically combine these two steps in only one. So you go directly, you have a map. At a high level, you would like to build a map which goes from data to already lower their parsimonious representations. Now, many methods, for example, in fluid mechanics, really hinge on the idea of projecting the data onto a low-dimensional manifold or subspace where the fundamental properties of your system are preserved. And to do that, of course, there are different approaches. There are some methods that probably some of you are familiar with that go under the name of dynamic mode decomposition for linear systems, and Kuhlmann theory, which extends these ideas to systems that are non-linear, which are very successful. They really build on a very, I would say, key concept, which is the one of proper orthogonal decomposition, which goes under different names in different fields. In control, has to do with the so-called principal component analysis. And it's really a way to detect coherent structures and fundamental structures in a system. But this has proven very successful in fields such as fluid mechanics, but less in more aerospace/control problems. And of course, there are various reasons for that. Two that we have identified are the following. The first is that these methods usually focus on autonomous dynamics. So you assume that you have a system that has some state x, and you only care about identifying x dot equal to f of x. So all you care is really how the state of the system autonomously evolve. But you don't have the concept of an exogenous signal, an input u that is perturbing your system. So the way this input will affect the system is not taken into account. And for example, Koopman theory, which builds on the idea of this Koopman operator that is proven to exist for a very general class of nonlinear systems, can miserably fail in case you have actuated systems. So it's enough to add a simple linear actuation, and certain nonlinear systems cease to have this Koopman operator, which justifies some more heuristic way of computing linearized models, which through DMD, for example. So the presence of an input is not just, let's say, an aesthetic addition. It's something that can really change the way you should go about identifying from data models. So this first aspect, I think, is quite key. So there is quite a difference if you want to get low order models with of system with input. And the second feature is that in aerospace applications, but not only, we have really an important feature, which is the effect on the dynamic of parameters, which are not states. So this is not simply capturing nonlinearity in a different way, but it's really the dynamic properties of a system change when parameters change. And this you can think, for example, in aircraft, there are some properties like natural frequencies that change with the flight speed. But this can also be the density, the altitude, and in other applications can be different parameters that change with time. And you don't need to find only a representation for one frozen, let's say, snapshot of the system, but you really need to find a collection. So a description of your system when this parameter is changing. And again, this poses challenges for the standard paradigm of DMD or POD-based methods that look at systems at, let's say, very well-defined conditions. So these two features that I think are inherent in many aerospace problems present challenges for the standard approaches. And in this algorithm, we really try to address both of them, of course, not in a complete way, but we try really to address these two shortcomings, and at the same time leveraging idea coming from POD and DMD. To put this in a more precise way, let's write down some equations. We consider high order nonlinear ODE, so systems that can be described in this fashion. This is a discrete time ODE. You can think of starting from maybe PD and discretizing space to get something like this, and this would justify, for example, why an X is so big, because it comes from a space discretization, and so you need to have a lot of degrees of freedom. X is the state, U and Y are input and output, and rho is this parameter that captures the fact that this F is actually changing depending on the value of rho. And our kind of wish list would be to get a so-called LPV low order approximation, where LPV stands for linear parameter varying. So given input state and output trajectories of this ODE, so we need to have access to, for example, a simulator or something that provides us these trajectories. We would like to find a low order LPV representation. You see, this is essentially a kind of a linear system in state space form, where F, G, H, D are, you can think as A, B, C, D in classic state space model representation, but with the key feature that this F, G, H, D will be function of rho, so they will not have a constant value. They are matrix functions, and we have two requirements. The first is that Z, which is the surrogate state that now has replaced X, needs to be low dimensional, so NZ must be considerably smaller than NX, and at the same time we would like to reproduce as accurately as possible the input-output behavior. So U, Y represent an input-output trajectory of this guy, and we would like to have this kind of same input-output behavior of this low-order LPV model, especially on unseen trajectory. So of course there will be using a learning nomenclature, a training phase where we identify FGHD, starting with these trajectories. But then, of course, we would like to have this approximation hold also on other trajectories that we have not used during training. So this is, at high level, what we would like to do. Well, of course, feel free to interrupt me whenever you want, especially if something in the problem formulation is not very clear. So just raise your hands and shout out. How do we go about this problem? So really the simplest approach that one can think of is dividing this problem in two steps. In the first, we would like to identify. So when I say identify, I mean basically computing an expression for these matrices I showed before, so FGHD, but treating them as LTI. So really dropping the dependence on rho. How do I do it? How do I do this? I just consider a grid of this vector rho, and for a fixed value of rho, everything now is parameter invariant because rho is fixed. So it's just like another parameter of my system. So I assume that I can look at my system for fixed value of rho. I excite my system, I get input state output trajectory, and based on this, I need to identify a low order LTI model, so a linear time invariant. And then in a second step, once I have this family of LTIs, I just interpolate them in order to get this matrix function FGHD. You can do linear spline interpolations. So this is a rather simple approach, right? But it actually hides some complications. The first is how do you define what's the best low order LTI approximation? So how do you even go about this step, even forgetting that you have other parameters? So we need first to agree on what's the best way to start from something that has dimension nx and then go into nz. It's not obvious. But in addition to this, the fact that you have now a family of rho means that this criterion that you choose to get the best low order LTI approximation needs to somehow holds in all the range. So you cannot decide to have a certain optimality criterion at one value of rho and then another value of rho will follow another criterion. You need somehow to be consistent. And this already starts posing some additional challenge compared to just doing the best low order LTI approximation of a nonlinear system. You need to find somebody that holds true across. And last but not least, the interpolation is not straightforward. If you just blindly or naively obtain LTI models that scatter value of this parameter grid, you cannot simply interpolate them, right? So if you recall like basic elements of linear systems, a linear system is not uniquely defined. You always have a similarity transformation that brings your state from one representation to another. So who tells you that you'll always be able to interpolate the state matrices? Because these state matrices are related to the coordinate transformation you used. So it's not even true that you can just interpolate them. Okay? If you're looking for an interpolation of the state matrices, which is useful in many cases. So this is a very naive and simple approach, but you need to deal with these well-known and standing issues. And our approach in this work is to build on the idea of a balancing oblique projection. I will say more in detail, of course, in the next slide, but really, if there's something you should take away from this talk is that projections there are different, there are like a zoo of projections. There are different ways to project data, and the use of oblique projection has several advantages. The use of balancing oblique projection, where balancing, for those that know a bit about system theory, has to do with the balance realization, and so with concept of controllability and observability of systems, really addresses these issues, we believe, in an elegant way. Because the two main advantages is that, on one hand, you answer this first question, what is the best low order LTI approximation, by saying that you want the low order approximation that preserves the input-output behavior of the system. So in other words, you will try to project data in that manifold or subspace where the most important connections between the input and the output of your model are preserved. And the second kind of class of issues is addressed by the fact that by using an oblique projection, which is defined by two set of matrices, as we will see, you will be able to get state consistency. So you will be able to interpolate these LTI models while at the same time not sacrificing accuracy, while using a parameter varying projection. So these last two issues are tackled by the fact that it's oblique. So balancing has to do with the input-output behavior preservation. Oblique has to do with the fact that you are more flexible in the projection, and so you will be able to capture more elements. The talk is really hinging on this concept of projection. So here I thought of just recapping for the general audience what I mean with projection and what is the difference between the orthogonal projection, which is probably the most popular, and the oblique one. Here we are considering projecting elements of finite dimensional spaces, so essentially vectors in Rn. So projections in this context are represented by matrices. And here I want to introduce two matrices through vectors. So given a family of R vectors, you can think of stacking them column-wise, and you get a matrix with R columns. For example, this matrix big phi is built by stacking column-wise this phi j. And similar for psi, you have r psi j vectors, so you have two matrices phi r, psi r, which define a set of biorthogonal modes, meaning that if you take scalar products, they give rise to basically this relationship. Okay, so projection is defined by a matrix, right? So we have two projections, two matrices, P prime and P. The first is the orthogonal projection, and it involves only one matrix, right? It only involves phi, for example, in this case. I could have taken without loss of generality psi, but for the orthogonal projection, you only need one matrix. For the oblique one, you need two, right? And you define them this way, with this matrix multiplication. And what does it mean? So this X is the element in this vector space that we would like to project, right? Think about, for example, a snapshot of the state of your system, so xk, the state at one time step. And we want to project. Over what we project? Well, we project over subspaces, which you can think as hyperplanes in a high-dimensional coordinate system, right? These subspaces are defined by span. So what I mean with span of a class of a set of vectors, well, it's any vector that can be described by a linear combination of these vectors inside span, right? So it is the classic concept that a family of vectors span certain subspace. So the subspaces we consider are generated by these vectors. So we have two subspaces in these figures. There is this horizontal one, which is span phi j, and this other one, which is span psi j. In the orthogonal projection, which is defined here with respect to phi, so with respect to these vectors phi j, what we want to do is to project x, this vector here, over the horizontal hyperplane defined by span phi j, okay? But in a projection, you have two information. One is where you project, where you land. The second piece of information is how do you go to that plane, right? That's not defined by the plane where you go. You can go in different ways to a plane. For example, in an orthogonal projection, you want to go to the horizontal plane by going orthogonally to it, so to say. Or more technically, you would go parallel to the orthogonal complement of that projection, or where kernel here denotes the null space of the projection, right? So if you look at P prime x, here it's really, you go from x and you draw an orthogonal line, so to say, or as I said, since this is in a higher dimension, you would go parallel to the orthogonal complement, but essentially you land in the horizontal plane in this way. In an oblique projection instead, what changes is the direction that you use towards moving into the plane. So you still land in the horizontal plane because kind of the plane where you land is defined by this first matrix, right? I think, I don't know if I'm mute. Okay, that's my fault. In this, the first matrix in this matrix definition defines the basis space, so the vectors that you will use to describe your vectors. So in both cases, you end up in the horizontal plane. The thing that changes now is that you are moving parallel to the orthogonal complement of PR, of a psi, sorry. See, so you are moving in this direction here, no more vertically. And as a result, you will end up in this point. So you have a projection on the same plane, but it gives two different points. That's the main difference. And of course, here you have a second degree of freedom. It's not all defined by the plane where you land, but also by the direction. And we are after these oblique projections today. Okay. This is an overview of projection. Now let's go back into our problem formulation. The idea is that we have this parameter rho, and we are already talking about LTI. How do we really formalize this? Well, you can think that for each fixed value of rho, which here I denote rho bar, you have an associated trim point, which is basically triple x, u, y that satisfies this relationship, right? It's basically a point at which your system is at equilibrium, which is a very classic concept in aerospace. Based on this, we can define so-called deviation vectors, which we denote with this tilde, and which are essentially difference between the current state or input-output and the associated trim point. Once we have this, we can formally define a linearization of the underlying nonlinear ODE with respect to the trim point, and we denote the states, input and output with this tilde notation, and the underlying state space representation with A, B, C, D. right? But of course, we don't have this because we don't have the model. So we cannot do just Taylor expansion and so on. This is just to fix the ideas. There is an underlying high-order LTI associated with the trim point and with F and H. What we have instead are so-called snapshot matrices. We have trajectories from which we can build snapshot matrices. So we have trajectories of length ns for each point in this grid that I mentioned before. And we can build these snapshot matrices, which are essentially matrices with nx rows in the case of the state, or nu rows in the case of the input. And then we stack column-wise all the instances of this sequence. And we have this at each point in the grid. Right? We have x0, x1, because these are just shifted version. See, this is x0 and this is x1. Other than that, they are basically the same. They have the same trajectory, but shifted by 1. And then input and output snapshots. Okay? So that's the ingredient. That's what we assume to have. And in the first step of our approach, we want to find these low-order LTIs. Right? We are still in the first step where we, for a moment, forget about the fact that we have parameter varying problem. So we are after this FGHD, where now there's not essentially row subscript, because these are constant matrices for now, assuming, which needs to be interpreted as low-order approximation of ABCD, because Z, if you remember, will have dimension nz, which is smaller than nx. And how do we do this? Well, we resort to this oblique projection idea, where now V and W are essentially replace phi and psi in my previous slide. Okay, so. Again, these are matrices built with by starting from vectors. So here I assume I have nz vectors. This will replace my r in the previous slide. And similarly, I define w, right? And V is called basis space and W test space. And V is really the basis space because its columns define the subspace where you project. So based on the columns of V, you can describe any point in this plane, because by definition, you are landing on a plane in which each point is a linear combination of this span. Okay, so the projection matrix is VW transpose. And the idea is now to describe, instead of describing the evolution of x tilde, we describe the evolution of z, where z is the vector of coefficients that linearly combines the columns of V in order to describe any point on this plane. Because once we give up the idea of describing x tilde in its full generality, and we are okay with just describing a projection of the state onto this plane, then it's useless to keep track of nx degrees of freedom. It's enough to only use nz degrees of freedom, because we know that everything can be explained by only nz coefficient, right? So this is the relationship. See, this x tilde equal to vz holds approximately, because remember, x tilde is the original deviation vector of the high-order linearized system. Of course, this is not true because we are looking at the projection of x tilde, but once we accept this and we believe that what we project will preserve the important quantities, then we can directly look at z. And the model you obtain as a result of this looks something like that, where I'm basically writing the structure for FGHD. So these four matrices are not something kind of black box, are something that have to do with ABCD, which is the original high-order LTI, which I don't know. And the structure really comes from these projection matrices V and W. Okay? So the interpretation of Z is this low-order state from which you can then lift up and retrieve x tilde. But the advantage is now you need only to simulate Z, which is lower dimensional. And this is a kind of a perspective of looking at FGHD as a function of ABCD, but of course you have the dual representation. So you can look at ABCD and think that actually ABCD can be described in this structure or low-rank way, right? You can decompose. This will be a huge state space model with a lot of degrees of freedom. But you actually can find a low-rank representation, which is the following. You have these projection parts, and then in the middle, something low-dimensional, right? So you have also this dual viewpoint on this dynamic. Okay, so this is kind of step one, at least at the high level. Step two is how do I get FGHD from data? Now, if you assume that you have V and W, the projection matrix, you know how to project, then you can formulate a simple linear regression problem where you are basically doing a least square in matrix variable FGHD, because you have these snapshot matrices, you have the projection, so you can just get FGHD and you have a closed form solution for this. You can think of adding, if you want, some regularization here and do a regularized least square problem, which has been shown to have various benefits to improve generalization and so on, especially if you have noisy data. But in its simplest form, you can just do this simple step. And here you have LTI, so we are still in the LTI realm, because we are thinking that now everything is frozen. What happens when I look more at the high level at my grid? So I'm actually now focusing a lot on rho is fixed, but actually I have rho scattered around. How do I deal with this? Well, you deal with this by recalling what's the interpretation of V and W. As I said before, V defines the plane where you project your data. So if you use the same V across parameters, then you will always have the same basis space, which means that the states will always be described with respect to the same transformation. So it means that you will be able to interpolate these FGHD models without losing anything, because you are basically projecting at each parameter value, you are always going onto the same plane. But since now you have a second matrix W, which defines the direction can be parameter varying. The direction will have no effect on the representation of the states. So you can use these two double degree of freedom in order to keep a fixed V and a parameter varying W. And by doing this, you get a parameter varying projection with state consistency. So the grid-based LPV reduced order model will look something like this. You have a certain grid on which you have these fixed models, and then you just interpolate them, as I said, with your favorite interpolation scheme. And now, if you want, well, the output of this LPV model will actually be, hopefully as close as possible, directly to the true output. But if you want the state, you can also inspect the states of your original high-order model by just lifting up Z by V. So at each parameter value of the system, you can just look at the current value of the low-order state Z, and then lift it up and approximately recover X in high dimension. Now, last but not least, of course, I haven't told you yet how to compute the Bayesian test spaces. I said, assume that you have V and W, then you can do all these nice things. But how do you actually get a meaningful V and W? Because without that, the whole thing kind of breaks down. And here we really use these system theoretic properties in the sense that if we are after input-output properties of the system, we know that the principal way to address this problem is to look into balanced truncation, which really boils down to exploiting the fact that I said before that every state space form is not unique, but can be basically equivalently redefined with respect to different coordinate transformation in order to put the states in a coordinate that is meaningful for input-output behavior. Namely, states are ranked in this particular balance transformation according to their controllability and observability property, which for the non-control audience, basically these two concepts, weights, controllability, basically tells something about how easy it is for the input to drive the state from any initial condition to any final condition in a certain amount of time. How is it easy for a particular state to address this problem? That's the controllability. The observability instead is how easy it is from just looking at the output to recover the current state, the state where the system started from. And these are two key concepts, of course, in control, because that's basically what you do. On one hand, you want to act on your system to drive the state. On the other hand, you would like to have an effect of that state on the output, and then you would like to use the output to do feedback. So capturing these input-output behaviors and these two properties is key. And so the idea of balanced truncation is, if all I care is this, why don't I put my state space in a coordinate where states are ranked based on this? So you will really have your state X ranked from 1 to nx, and the first is the most controllable observable, and then so on with the others. And then once I have this, which is just a transformation, doesn't change the order of the system, now I just drop the last nx minus nz states. So the ones that I care least, I will just drop them, because I know that the input-output map will be substantially the same. Of course, the amount of states that you need to drop depends on some well-defined quantitative property, which go under the name of Hankel singular values of the system, that really are a list of positive numbers that tell you the degree of controllability and observability of each state. So you can plot them, and then once you have an idea of what, in your opinion, is enough to describe the input-output, then you drop all of the states that are below a certain threshold, right? This is great, but the problem is that it's model-based, right? Because the way it works is this matrix T has to do with so-called balancing and adjoint modes, which depends on quantities called gradients, which at the end of the day are functions of ABCD. So the way balance truncation works is you give me ABCD, I compute these gradients, from these I compute these modes, from these I compute T, I do this, and I do balance truncation. And this is what it's implemented in BAL-RED, for example, in MATLAB. Now, here we have two problems. The first is that we don't know the model. The second is that it's very difficult to compute these quantities when X is high dimensional. Even if we had the model, it would be a very ill-posed problem numerically, right? But the good thing is that if you observe how this transformation is defined, and you look at T, the expression of T and T inverse, these are not some random quantities. These are really matrices that are related, that we have already seen in the previous slides. So essentially, if you replace this here, you see that this is essentially an oblique projection. So you can interpret balance realization, which is technical name to say go from any state space form to a balanced one, as an oblique projection. And so now you see where I'm going, which is I want to use data in order to compute V and W, and I know that V and W are related to these gradients, because I know that in model-based balance truncation, these transformation matrices, which are nothing but these matrices defining the projection, are related to the gradients. So if I have a numerically stable way to compute empirical gradients from data, I can then compute Bayesian and test spaces. Okay? And luckily, there are some methods in the literature that address these steps kind of independently. So there's some method to compute empirical gradients, which is probably the most challenging step, because these quantities really depend on ABCD. But exploiting the structure of linear systems, you can obtain gradients from ad hoc simulations. Here with ad hoc, I mean that you cannot use any input you want, but you need, for example, to get the controllability, you need to excite the system with an input response. And to get the observability is a bit more tricky, because you are required the adjoint model. If you don't have that, though, you can still perturb the system starting from certain initial conditions and get these, the observability gradients. So there is a way to get these guys from data without knowing the model. On the other hand, once you have these gradients, these are kind of high dimensional, so it's not really, this step, it's okay, even if it's high dimensional, because this just comes from aggregating simulated data. So there's no numerical ill-posed step here. What becomes a bit more ill-posed is in computing this balancing and adjoint mode that are nothing but another word for this V and W. And for this, we use also here some interesting work that looked into this problem of finding tractable ways, but in the model-based case. And here we adapted to the data-driven case to essentially make these steps affordable also for high-dimensional systems. So once we have this, we have V and W. The missing part is how do you choose NZ, which is the order of the low-order model. And, well, you can actually have two ways. Either you fix it a priori, you say I want the model of certain size, but the more, I would say, engineering way to decide on this is to look at these Hankel singular values, which is what I mentioned before. That somehow gives you a measure of what needs to be the dimension of the subspace where you project. Because for some systems, controllability and observability are described by a handful of states. In that case, you don't need to preserve a lot of states in this projection. It might be enough 4 or 5. For others, it's different. But the good news is that this procedure here also gives you empirical Hankel singular values, which empirical because, of course, the original ones require ABCD, but you have a way to approximately compute them. And so you have a very good guideline on how to choose NZ. So at the end of this procedure, we end up with this V and W at each grid point. V will be computed actually fusing information coming from different parameters, because I said that V is constant, and you might say, how do you choose it if it's constant? Well, there is a way to blend the information coming from different green points in one constant matrix, and so we do that, whereas for W we can preserve the flexibility of essentially using them at the different points. So this is just a summary of the procedure. So we leverage the fact that we have input-output trajectories. From this, on one hand, we compute this Bayesian test space for the projection. On the other hand, we do the regression. So we use data in these two steps. And in the end, we get for free the interpolation because it's all state consistent. So as far as we were aware, this was the first data-driven algorithm for LPV models that have these two properties. So you have state consistency while having a parameter varying projection, so not giving up projecting based on information of each parameter, and also using the idea of balance projection. Of course, this is not the panacea and it's not all good. There are still technical limitations. Here I'm just mentioning two. The computation of test and basis spaces is definitely the most delicate part. And also the fact that the training data must include state trajectories implies that you need a simulator, right? So the whole point of saying the system is too complex to describe, let's go for data. Well, but who's giving you the data here? It's again a simulator. So this is probably, for me, at least conceptually, the strongest limitation. What I would like to see is a fully input-output method where it's much more reasonable because then you can use experiments. In this case, the states of the system are still synthetic data. And for this, we have explored we explore connection between subspace identification and POD-based methods, which can provide, I think, interesting insights for both these improvements. Now here I just wanted to give an overview of two methods with which we benchmark our algorithm, and I wrote them in the same notation that I use for BMD. You see that in this paper, basically they were proposing a fit for FGHD by solving this problem. Now if you look at the difference is that here they are using Q, a single matrix Q, instead of V and W. Essentially what they are doing here is an orthogonal projection. So it's like what we are doing, but deciding to do an orthogonal projection on not balancing modes, because of course to do balancing you need an oblique projection, but on the set of so-called POD modes, right, which are basically obtained by taking the snapshot matrix, doing an SVD decomposition. These are the left singular vectors. You take the first NZ vectors. This would give you Q, which is the matrix with the first POD modes. And then you do an orthogonal projection. So at the conceptual level, you end up with a system like this. This just to bring up the analogy with what we were doing, but now you only have Q. If you remember, in orthogonal projection, all is described by Q, so you go orthogonally over it. And this is, if you want, the natural extension of DMD to the input-output setting. There are two shortcomings associated with this approach, in our opinion. The first is that the projection on POD was the interpretation. I gave you the interpretation of projecting on this using balance projection in terms of input-output behavior. Projecting on POD, as many people in the audience know already, has to do with projecting according to the modes with higher energy content, which is very favorable in applications such as fluid mechanics, where you can really identify some vortex structure or some really meaningful behavior. But in input-output models, this is not necessarily the right thing to do. And there are numerous counterexamples in the literature that, for example, prompted the idea of a balanced POD. So this was the first shortcoming. The second shortcoming has to do with the LPV. So they were also considering an LPV model, but since they were using an orthogonal projection, they only had one matrix. So what they had to do in order to get state consistency was to use the same Q across all parameters. So somehow they were also fusing information coming from different parameters, but at the end of the day, because they wanted an LPV models with state consistency, they had to use the same Q. And of course, that makes you lose even further, because the optimal way to project can be really parameter independent if your system is parameter varying. So these were the main shortcomings. The second one is really similar work. They were also extending DMD in the direction of input models. And essentially, it's very similar to the previous method. The only difference is that they were not really interested in LPV models, which are very useful for control, because there is a whole class of robust control that deal with the problem of identifying controllers for a model in LPV form. they were more interested in prediction or using these models for other control applications. So essentially, they gave up state consistency. They didn't have a proper LPV model. And what they were doing was just to interpolate directly the state. So I show you that you can always lift up the state by just doing this thing, right? So you run your lower order model, and then if you multiply by Q, you go back to the high dimensional, where of course you have state consistency, because the original state is only one, right? But to do this, you need to run in parallel basically all your lower order models, and then depending on the value of rho where you are, you need to find an interpolation directly of the state. So in addition of not having a state space model, you also need to interpolate on the fly the state. And so this was the second kind of algorithm that I wanted to introduce, just to say what's the state of the art, and also to prepare for these numerical results where basically we compare these algorithms on this morphing wing. So it's a wing where you try to have aileron and elevator actuation by morphing of the trailing edge. And this was also experimentally tested by these colleagues from ETH, and so this FSI solver that we used was kind of realistic in the sense that was matching the data, at least for some set of experiments. The model had around 600 states with 6 inputs. These are angle of attack and rotational velocities, which are here because basically this model only describes the wing, and it's supposed to be coupled with a flight mechanics model, which would provide this input, so that then you have a full kind of system more realistic than just looking at the wing. But at this stage, it was still not coupled, so we had this as input to the model. And then FS and FAS are basically symmetric and antisymmetric actuation that you obtain with this morphing. So we consider different options for why you can look at different type of output of the system, and rho for us was the flight speed. And this is being used for airborne wind energy application. So here I have a handful of comparisons where this is for the parameter fixed case at different speeds, because of course these are methods that you can also use in the LTI setting. You don't need to have parameter variation, you just leverage less the advantages, but you can also use at fixed values. And here we were considering, basically in these plots you see on the x-axis the model size, so NZ, and on the y-axis it's a measure of the prediction error. So we do the training, and then we excite the system with different set of inputs, here sinusoids, and then we compare with, of course, with the FSI solver, and here you have a measure of the relative error, and you have 3 curves. For each value of NZ, you have 3 points, and basically you go from ADMDC, IO, ROM, and BMD, and you see that after a certain value of NZ, basically these methods all do pretty well, but if you want a very low order representation, you see the advantage of capturing this input-output behavior with respect to just looking at POD modes. This is instead for a parameter varying case where we change the speed from 20 to 50 with constant acceleration. And here we have 3 plots because we excite the system with 3 classes of inputs: sinusoid, chirp, and PRBS, which stands for pseudo-random binary signal. And it's a way to explore all the frequency range of basically a system. So it's a very informative output signal. And here we are also changing the kind of parameter variation. I would say here again, BMD seems to outperform the others with a few exceptions, and there is also the kind of trend of these methods becoming very close as the order of the system increases. These are just time domain simulations. So here I was condensing all the time domain thing in one point for different NZ. Here I fix the NZ and I'm showing the time domain simulation. Here for aerodynamic coefficients. Here I was showing the first bending mode amplitude, so different outputs, but same inference. So here again, BMD capture better the FSI solver. And then the last thing I wanted to show is an application to control, because what do you do with these models? You can do prediction, but you can also do control. If you have an LPV model, you can do LPV design, but even in ADMDC, where you don't have an LPV model, you can use the prediction to use a very popular control technique called model predictive control, where the idea is to solve an optimal control problem in a receding horizon fashion. So you write down here your cost function that you want to minimize. The constraints can be input or output constraints, and crucially you have the dynamic, right? Because basically your output will be a function of the input. And here you want to optimize the input to minimize certain cost, which is typically blending the energy that you need to spend to actuate your system with a performance criterion. For example, tracking a certain profile, right? And you're trying to do this in an optimal way. But crucially, you need a model. It's called model predictive control because you need a model to predict what's the effect of your input on the system so that you can optimize over your input channels. So having accurate models is key in order to then get also nice closed-loop performance. So we compare these three algorithms, and here you just see some problem definition. On the left, you have basically the flight speed profile. So this is the red curve is how rho is changing in this mission. And then you have disturbances, turbulence, and gust acting on the system that is basically making the controller life more difficult, because that's what in the end feedback is useful for, to counteract disturbances that you haven't taken into account before. And on the right, you see the two profiles that we want to follow. This is like a lift profile. So we want, for example, in one case, we want to track a certain lift profile to maximize, for example, the output generated with this highway system. And in red is another mission where, for example, we want to track a certain bending mode profile. Here it's, especially the red one is more notional. It's not clear why you would like to do that, but it's to explore what's essentially the model capability in telling you what's the right thing to do in order to track this kind of profile. So it's more to explore the capability. Whereas for the lift, I think it has a clear highway meaning. So you want to maybe maximize a certain power of your system, and you know from some calculations that you have a certain lift, and that's what you should do. And here again, I'm showing as a function of the model size was the closed loop cost. And essentially, you can see that the lift tracking problem was kind of easier. So the difference among the algorithms is less marked. But in the bending one, you see again a trend for BMD, except for a few points in giving better prediction. And I have to say that the points where BMD was not doing that well are really related to the basis and test space calculation, which sometimes prove numerically ill-posed and can give rise to more inaccuracies. But overall, you see the same trend of even in control application of really having a benefit of using these ideas. Last shout out to the kind of, we have recently posted this, we have made this repository and we have submitted something to the Journal of Open Source Software to make these three implementations freely available. So in this package, you get on one hand the FSI solver, which is a solver coupling FE method with an steady panel method to generate data of two parameterized wing models. But of course, this can be augmented with other wing models or simply ditched. This is just the kind of data generating part. And then you have a part of the repository which implements these three algorithms. So you can look at the implementation. And the idea is both to kind of advertise this method, but most importantly, to offer a way to benchmark in case you are working on new data-driven algorithm or you want to test them for your application. It's an easy way that avoids you re-implementing all the stuff. So you are, of course, you are free to visit there and get in touch if you have comments. These are the conclusion. The idea was to show this data-driven algorithm that presents some novel aspects and probably create some room for discussion and food for thought, in the sense that I really wanted to emphasize the three main differences with the state of the art in the direction of bringing system theoretic properties in data-driven approaches. And I hope at least the main message came across. And finally, I show some result on a morphing wing demonstrator. As an outlook, of course, there is a technical outlook which is addressing some of the current limitations that I discussed before. And then the other, of course, direction is to apply this to more control problems, and especially to more aerospace applications, maybe more challenging ones or just different, to see how this idea of using oblique projections work in different contexts. Because, of course, it might be application dependent. These are some references I touched upon during the talk, and the talk is mostly based on these two papers that were, I think, also mentioned in the abstract. And again, this is the repository that, you're welcome to visit. And yeah, with this, I'd like to